Hi, this is Moser with a quick tutorial on isotopes, also called What a Difference a Few Neutrons Makes. So, after this video, you should be able to identify isotopes of any element and write the name of any isotope in either of the two common formats. You should also be able to calculate the average atomic mass of any element based on the mass and abundance of its common isotopes. What you need to know before you start this video is the three major subatomic particles and their relative masses, as well as how to use the periodic table to find the number of protons in any element, and how to use the periodic table to find the average atomic mass of an element. But I think you have that, so let's get moving. This is the part you know, that atomic mass is equal to the total number of protons and the total number of neutrons, because of the fact that we assign the proton and neutron each a value for their mass of 1 AMU. So 1 proton contributes 1 AMU of mass, 1 neutron contributes 1 AMU of mass. That's easy enough. What you may not have known, or maybe you did, is that not all atoms of a given element have identical masses. While any atom of a given element has to have the same number of protons, because changing the number of protons would change the identity of the element. So carbon always has 6 protons, it can't have 5, it can't have 7, and 8 is right out. However, the number of neutrons present in each carbon atom doesn't change the identity of the element. It does change its mass, though. So we have a lot of carbon atoms that have 6 protons and 6 neutrons. They have a mass of 12. So carbon with a mass of 12 is oh so creatively called carbon-12. We also have some carbon atoms that have 8 neutrons. That carbon has a mass of 14 AMUs, and it's called carbon-14. So that's simple enough. For any one of these isotopes, you can figure out how many neutrons are present by subtracting the subtracting the atomic number, or the number of protons, from the mass number. Okay, pretty straightforward. Now, there are 2 common ways to represent a particular isotope of any element, and the first one we've actually just done here on the last page. That's hyphen notation. And we do hyphen notation 2 ways. One is by writing the full name of the element, such as nitrogen, followed by a hyphen with the mass and AMUs of the isotope after it. So this is the name for nitrogen-15. It's an isotope of nitrogen that has a mass of, oh, don't you dare get this wrong, 15 AMUs. The other way we use hyphen notation is to write the symbol for the element, followed by a hyphen and the mass again. This is another way of writing nitrogen-15. Pretty easy. The slightly more common notation that we'll find in scientific writing is called symbol notation. So we start with the symbol for the element, and at the top position to the left of the element, we write the mass. Now, in case there's any question about what element we're talking about, down below on the left-hand side, we write the atomic number. It provides a double check, and it also gives us a very fast way to see how many neutrons are in this substance, because of course this is the number of protons and this is the mass. So 1 atom of nitrogen-15 would have 8 neutrons. Okay, that's pretty easy. Now comes the slightly more complicated part. If we can't have a half of a carbon atom, why are the atomic masses given on the periodic table not whole numbers? I mean, they're clearly not. They're decimal values. So how is that possible? We can't have 0.010 of a carbon atom. So what do these mean? Well, they're weighted averages. A standard average doesn't account for different numbers of a given thing. Whew, that was rough. When we average 3 numbers, we simply add up our numbers and divide by the number of things there are. Well, that's pretty easy. You know how to do that. But this says there's only 1 value of 72, only 1 value of 83, and only 1 value of 77. What if we had a few more? What if I, in fact, had 5 values of 72, 2 values of 83, and 3 values of 77. How would that change things? Well, first off, it would change the number I'm dividing by because I have 10 total values, so I'm going to divide by 10. Okay, well, I can add these things all up and divide by 10, and that'll get me an average, but wouldn't it be easier to do this? I can multiply each value by how many times it appears, add those up, and then divide by 10. This is equivalent to doing this. Well, let's take this one step further. So this is mathematically equivalent to this. Interesting. Because we can distribute that division by 10. Well, that's all mathematically equivalent. Well, what do you know? This is mathematically equivalent to that. This is called a weighted average. And instead of adding up all of our numbers and dividing by the total number of entries, we're going to multiply each value by the percentage of entries that are that value. It's a whole lot cleaner. Let's do an example with a weighted atomic average. So let's take silicon. You got your periodic table handy? Its atomic number is 14, so it's got 14 protons, and there are 3 isotopes of silicon that we find in nature. The first is silicon-28 with a mass of 27.976 AMUs, we very often just say 28, and an abundance of 92.23% of all the silicon known on the planet. Silicon-29 has a mass of 28.976 AMUs and makes up 4.68% of all the silicon known on the planet. And we have one more. That's silicon-30 with a mass of 29.973 AMUs, making up 3.09% of all the silicon known on the planet. So how do we figure the average atomic mass considering all of these isotopes? Well, let's set that up. The weighted atomic mass for any element is the percentage of the first isotope times its mass plus the percentage of the second isotope present times its mass plus the percentage of the third isotope present times its mass. And we can do this for as many isotopes as exist. In some cases there are 2, in some cases there are 5. Some elements have 7 or 8 common isotopes. So let's set this up for silicon. Okay, so I've laid out the percentages times atomic mass for each of my 3 isotopes, and I want to point something out quickly. Note that I've put the percentage over 100 because that's what percent means. It means pieces per 100 that would have that mass. You're welcome to just go ahead and move the decimal if you feel like that won't screw you up. Here's where I screw it up. I'm okay with 4.68%. I tend to screw up when I have 0.17%, 0.46%. So I like to put these over 100 as a way to error-proof myself. Let's get a raw number. Okay, we have a raw answer of the weighted average atomic mass of silicon being 28.0845 on and on and on and on AMUs. When we check a periodic table, we show silicon with an average atomic mass of 28.085 AMUs. Not too shabby. Okay, you should go off and look at the practice on your own. If you still have questions, I'll have a series of follow-up videos with additional problems of this type to help you. And I'll also be linking a really handy interactive periodic table that gives you the mass of the common elements as well as their abundance. See you later.